In this video today, we're going to be talking about how some of the variables can look a little bit different in just some of their names, or the symbols that we use to represent them when we're talking about vertical motion versus horizontal motion. One of the big changes we'll look at is how instead of using the label X, we'll start to use the label Y. And then also, instead of just using the label A, how we can use the label A sub G or G for acceleration. All right, and we'll go through and talk about why that is. This will lead us into our work this week in the sense that we will be using equations tomorrow in class to solve for displacement vertically, time in the air when we launch something vertically or throw it into the air, or if something drops from a higher position to a lower position. Let's start off with looking at just part of a Cartesian plane. Now, what we've become familiar with is that the horizontal axis on that Cartesian plane is labeled X, and the vertical axis is labeled Y. So if I start at point A and moved horizontally, and I move from A to B, what we've said before is that this is labeled delta X. However, since now we're talking about moving horizontally, if I move from position A to position B, then what we can call this now is, instead of delta X, because that's for horizontal motion, we can call this delta Y. Now, delta X is just the difference between where I ended, let's say X final, to from where I began. Let's call that X initial. So basically, if I take my position at point B and subtract it with point A, then I'm going to get my displacement. And the same thing is true for delta Y. If I take my final position, I can call it YF, and subtract it with my initial position, let's call it YI for initial position, then we can get what's called delta Y, which is our displacement. In other words, displacement is just the difference in position from one point to another. And that's what we're looking at, whether it's horizontal motion or whether it's vertical motion as well. So the big changes that occur here is that in our equations, any place that we have delta X, and I've circled those here, those can be rewritten as delta Y. And the only reason that we're going to relabel those delta Y is if we are talking about using these equations for an object that is moving vertically. So X was used for objects that are moving horizontally, Y can be used for objects that are moving vertically. So the equation stays the same, it's just a different letter that we're using to represent that it's vertical motion. Now, let's include A with this. And acceleration used to be that we were accelerating based on something that a human would do. So if a human speeds up a car, or if I push harder, then I can accelerate faster. Well, we learned about acceleration due to gravity the other day, and we found that this was the value for acceleration due to gravity, 32.14 feet per second squared, or 9.8 meters per second squared. Now, I use the letters AG, and the reason I use those letters is because when we're talking about vertical motion, our acceleration is being affected by gravity. So when I throw an object upwards, I'm not giving it any sort of acceleration. Gravity is controlling its acceleration. So when I throw something upwards, it's gravity that's slowing it down at these rates, and it's gravity that in turn speeds an object up as it falls back to Earth at those rates, 32.14 feet per second squared and 9.8 meters per second squared. And the big thing to recognize is that instead of just calling it A for acceleration, we're going to call it AG for acceleration due to gravity. And since gravity works downwards, then these can be labeled as negative values, since it's a downward vector or negative vector. So any place that I have A for acceleration in my equations, I can change that to A sub G. Now, sometimes people call this just G, and we can get to that in a second, but let's rewrite our equations now. So this top equation can be rewritten with delta y a sub g, and the equation's the same, it just tells us that now we're talking about vertical components, vertical motion. And the same thing with the rest of our equations. It doesn't change the equation, all it does is identify that we're talking about vertical motion and objects moving in vertical motion. Alright, so now that we've rewritten our equations, I'll just throw out there that sometimes people don't use the letters AG, sometimes they just use the letter G. And G can be an accepted letter to use instead of A sub G, and G just stands for gravity. In other words, the acceleration due to gravity. Okay, so let's take a look at how this works in a problem, and let's include all of our equations, and I wouldn't call them new equations. They're the same equations we're using before. The only difference is that we're talking about vertical motion, so all my delta x's have been replaced with delta y's, and all my a's for acceleration have been replaced with a sub g's. Alright, so Chuck is riding the giant drop at Great America. If he free falls for 2.60 seconds, what will be his current velocity and how far will he fall? Now this is a vertical motion problem, so that's why I'm going to be using these versions of those equations to represent all of the variables that are occurring vertically. So I'm going to first draw a picture of what's going on, and I'm just going to use a box to represent this because I don't really care what the giant drop ride looks like or what Chuck looks like. I just need to know that it's an object, and a box is a pretty easy way of drawing that there's an object there. So the object is traveling downwards, and I know that the time is 2.60 seconds of travel. And actually I'm going to move that over here because time doesn't really have a vector with it. So to put an arrow next to time is kind of can be kind of confusing. So I know it's moving downwards and it has 2.6 seconds to free fall. Alright, so my acceleration due to gravity, I'm going to use the metric system, is 9.8 meters per second every second. Now I'm going to say a negative 9.8 because it's a downward vector. It's pulling things down. And on a Cartesian plane, anything moving down is considered to be a negative. Alright, so it's moving downwards. I'm going to extend my arrow there. And it moves from what I'd call its initial position, yi, and it moves to its final position, yf, in that 2.6 seconds. And the two of those together creates what we call delta y. Now I know my initial velocity is 0 meters per second because it's in free fall. So it started from a stopped position, and then free fall means that we're not speeding it up as it travels towards the ground, it's just free to fall. And gravity is the thing that's speeding it up from a resting position. Alright, so I know that I'm trying to find my final velocity because that's in the question. What will be his current velocity after he free falls for 2.6 seconds? But it's also asking how far is he going to travel in that 2.6 seconds. So I have two things that I'm looking for. What I'm going to start with is by finding my final velocity, and then I'll use that information to find my displacement vertically. So I'm going to list all my variables, and I'm going to plug in what I know about my variables. And I'm going to put a 1 next to this question mark because that's the first thing that I'm going to figure out. And then here's my acceleration due to gravity, here's my time. And then I'm going to put a 2 next to this question mark because that will be the second thing that I figure out. Alright, so on my piece of paper, I could cover up the second thing I want to figure out so it's not maybe distracting to me. And I'm just going to focus on these 3 variables I know and the one that I don't know. So now I need to find an equation that will help me find final velocity and that doesn't have displacement in it because I've covered that up and I need to find that later on. And the only equation I can see is this one right here. So I'm going to plug in my information. These are the things that I know. So nothing has changed from what we've done with horizontal motion. I can ignore the 0 meters per second. I'm going to multiply those together, and my units come out to be meters and seconds over seconds squared. Well, the second on top cancels out the second on the bottom, and I'm left with a final velocity which is equal to negative 25.48 meters per second. Now some of you guys are going to say, okay, well why did I get a negative 25.48 meters per second? Well, first of all, we're multiplying a negative acceleration with time, and that gives us a negative velocity. But you also have to remember at what direction this object is moving. It's falling down, which means that its velocity, which is a vector, is also moving downwards in this direction. So anything moving downwards on a Cartesian plane is a negative value, and the negative just gives us a sense of direction. Alright, so now that I've figured out what VF is, now I know 4 variables out of 5, and now I can uncover my second part of the problem, and now my goal is to find delta y. Now, I can choose any of the 5 equations on the left side here that include delta y with them, and I'm using the word delta y because we're talking about vertical displacement or vertical motion. What I'm going to do is choose the easiest of the 4 equations that I could use, but what I'm going to challenge you guys with is if you use the other 3 equations that have delta y in them, you're going to find that you're going to get the same exact answer. So no matter what equation I use from this point on, I would get the same answer. So I'm just going to use the easiest looking equation, which is this one. So I'm going to plug in my variables. Here's my final velocity. Here's my initial velocity. Divided by 2. Those will be added together, and then I'm multiplying by time. So I'm going to do what's in parentheses first, and that just comes out to 25.48 meters per second multiplied with time and divided by 2. Now I'm going to multiply time with what's inside the parentheses, and I should see that my seconds cancel out, and I'm left with just meters on top, and divided by 2, and this gives me 33.12 meters, and that's a negative. Now again, you guys might say to yourself, well, why is that a negative? And let me write it in here, and then we'll answer that question. It's a negative because, again, we are moving downwards, and displacement is also a vector, so that gives us a direction. It's saying I went 33.12 meters, or I moved 33.12 meters down. And the way to show that mathematically is delta y is just 33.12 meters from my starting position to my ending position. So if I put that into my equation for delta y equals where I ended minus where I started. So that is 0 minus 33.12 meters, and delta y is negative 33.12 meters. So it all works out. So what we've shown here is that some of our variables change the symbols that we use based on the fact that we are talking about vertical motion. Everything else stays the same. The symbols may change a little bit, but the equations are the same, except now we're just using them for vertical motion. And something that we're going to get into a little bit more is this idea of these negative values. So using negatives to determine if something is moving up or down. And side to side. And with vertical motion, when anything is moving downwards, then we can count these things like velocity, acceleration, displacement as potential negative numbers, because all of those are vectors, and when a vector moves downward on a Cartesian plane, then we represent that number as a negative. So that negative shows a direction. Alright, tomorrow we'll work on some problems in class to practice this. It's all the same equations, just some different symbols, and we'll end class tomorrow with an exit ticket and see how it goes from there.